In this video, I want to talk to you about Ksp. So what Ksp is, it stands for Solubility Equilibrium. And it's very similar, if not the exact same, as Kc and Kp. The only difference there is when we're working with Kc, we're working with concentrations, right? When we're working with Kp, we're working with pressures in ATM. When we're working with Ksp, we're working with concentrations as well, but it's a very specific type of concentration. We're dealing with a solid that's being broken apart into its ions. So we have an aqueous thing here plus another aqueous thing here. So that's supposed to be AQ. So Ksp means that we are finding the equilibrium for a solid dissolving into its ions. And how do we do this? Well, essentially, how we get a solid to dissolve into its ions is by sticking it in water. So that's what we're dealing with here. Now, I know that you're going to freak out when I say this, but let's refer back to our solubility rules, okay? If you don't know your solubility rules, you might want to go over them again, okay? So that's talking about, like, what's the rule for chlorides? What's insoluble for chlorides and all of that stuff? Well, when we're dealing with those solubility rules, there's a little margin, a bit of wiggle room, I guess you could say. And when we say something like AgCl, right? So for instance, AgCl, we say that it's classified as insoluble, right? And so what that means is that that insoluble thing will remain a solid inside in my container. So we'll have a precipitate there. Well, what we didn't talk about in the solubility rules is that you will have a little bit of that stuff being soluble, meaning that a small portion of the solid will break into its ions, okay? So Ksp is the relationship of how soluble these solids are when we refer to our solubility rules. So when we're working with Ksp, we're going to be working with those things that we classify as insoluble in our solubility rules. So this is how that's connected. Now, the way that we write Ksp expressions are almost exactly like we write our Ksp or our K expressions for equilibrium. So what we have here is the reaction AgCl breaks into Ag plus Cl minus. Now, if you remember from the other equilibrium videos, pure solids and pure liquids are never included in your equilibrium expressions. So this is why these Ksp expressions look a little bit different, because it's always a solid breaking into its ions. So the way I write these Ksp expressions is I only plug in the aqueous things. So it'll be Ag plus times Cl minus. Now, what if I had a 2 coefficient? Well, I still raise it to the 2 power, if that's the case. So the way I write my K expressions are no different from before. The only reason why they look a little different is because you're always going to be starting with a solid as your reactant. So you're never going to have anything on the bottom of your Ksp expressions. I hope that makes sense to you. All right, so let me pause it. I'm going to scoot to the next page, and we're going to talk a little bit more about Ksp. So what you see here is Ksp values for a whole bunch of different stuff, okay? So we have things that are fluorides, carbonates, sulfates. These are all solids, and we have different Ksp values for that. So we can relate this to how soluble a solid is. And remember what solubility means. Solubility means that that solid is breaking up into its ions whenever you put it in water. So we want to do some practice here, and we want to write our Ksp expressions for all three of these. So we'll do these together. So for the first one, we have CaF2 solid breaks into Ca2 plus 2F minus. Now, one thing that you will have to be able to do is write these equations on your own. You might only be given the solid here, so you might have to finish the rest of the equation. Well, all you're doing is splitting up your solid into its separate ions and then balancing the equation accordingly. So if you don't know the charges of your ions, you better get to reviewing that. So I want to write the Ksp expression for this. So I get Ksp is equal to products, which would be Ca2 plus, raised to its coefficient, so this one is just 1, times your other product, F minus, raised to its coefficient, which would be 2, over your reactants. Now your reactants, if it is a solid or a liquid, we don't include it. So that's why this is your Ksp value. If I want to write the Ksp for this one here, you see again a solid. You see here a solid. Do you see how all of your reactions are just your solid breaking into ions? So the Ksp expression for the second one would be Ag plus squared times CrO4 2 minus. And for the last one, it will be Ca2 plus times C2O4 2 minus, and we don't raise to any coefficients because I don't have any coefficients here. So this is how we write our K expressions. So when I'm working with these, I set them up in rice charts just like I have before. So PbCl2, we don't worry about solids in our equilibrium expressions. So all we're worried about are these ions because that's what goes into my K expression. So I refer to my particular x's and all of that. So this is going to be plus x, refer to the stoichiometry there. This is going to be plus 2x. And so my equilibrium expression is going to be x here and 2x here. Now, for this particular example, let's start by writing our equilibrium expression. So Ksp is equal to concentration of Pb2 plus times concentration of Cl minus squared. Now, let's see if there's any information. We want to figure out our Ksp. There has to be some piece of information to tell us what X is. And so it tells me that the lead concentration is 1.62 times 10 to the negative 2. So this is my equilibrium value of lead. Well, my equilibrium value of lead is just X. So this is the value of X. If I want to find the value of 2x, I would take 2 times this value. So I'm going to plug in Pb2 plus, which is 1.6 times 10 to the negative 2. I'm going to plug in Cl minuses, which is 2 times x, which is 3.24 times 10 to the negative 2. And I'm going to square that value. And once I do that math, I get your value for Ksp, which is 1.7 times 10 to the negative 5. So you see how this is no different from what we've been working with before. You set up your rice chart. This solid will always not be in the equation, so we don't have to worry about it. These will initially be 0. You have x, you have 2x, just like we've done before, and it's giving you the piece of information that tells you the equilibrium value of Pb2 plus. So now that I know what x is, I plug in x there, and I solve for my Ksp. Now, one extra thing that's dealing with this is they like to use a terminology. Remember how we were talking about a percentage of a concentration or a percentage of a thing? That's a code word for your X value. Well, they kind of had a code word for your X value for Ksp as well. And that code word is solubility. So whenever you see the word solubility, that is giving you the value of X. So this X value has 2.0 times 10 to the negative 4th. Now we know that we're dealing with copper 1 bromide. So we have to write out that reaction first. So copper 1 bromide would just be CuBr. So if you don't know how to write this stuff out, You need to practice it. That's a solid. It'll break down to be copper plus Br minus. Now we write our Ksp expression. So Ksp is equal to Cu plus times Br minus. That's Br minus right there. And now we plug in our rice chart. The solid we don't care about. This is 0. This is 0. This is plus x. This is plus x as well. And so my x value is given to me, solubility. So that means that this is going to be 2 times 10 to the negative fourth. This one is also going to be 2 times 10 to the negative fourth. And so now all I do is plug these two values into my K expression. So Br minus and Cu plus. Those values are going to be plugged into my Ksp expression, and you'll solve for your Ksp, which is 4 times 10 to the negative 8th. So you see how this is not any different, except X has a code word, and that code word is solubility. Let's do another example problem. So for this example, we have Ksp for bismuth sulfide, so that's Bi2S3. So let's first write our reaction. Bi2S3. That's a solid. Breaking into the ions. So we're going to break into both of these ions. You uncrisscross your charges. So bismuth is going to be a +3 charge. And your sulfide is going to be a -2 charge. So this is back to chemistry 101 if you don't know how to write this crap. Now we have to make sure our reaction is balanced. So there's 2 bismuth there, so I need to put a 2 here, 3 sulfurs here, so I got to put a 3 there. Now let's finish out our ice chart. So 0, 0, plus 2x because of the 2 coefficient, plus 3x because of the 3 coefficient. So I know this is 2x, and I know that this is 3x. So now, let's write our Ksp expression. So our Ksp expression is going to be Bi3 plus, that's 3 plus, squared, times S2 minus, that's cubed. So now, we figure out if we have some information to help us solve for x. So it tells me solubility, remember that's x, is 1 times 10 to the negative 15th. So what I'm going to do here is say 3 times that value is equal to 3 times 10 to the negative 15th. 2 times that value is equal to 2 times 10 to the negative 15th. Now that I know what my equilibrium values are for both of these, so this is my equilibrium value for this is my equilibrium value for this, I'm going to plug that in. So I take that value squared times this value cubed, and that gives me my Ksp value, which is 1.1 times 10 to the negative 73. Now you see how this is a very, 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 very small number. The smaller your Ksp value, that means that it's less soluble. So the chances of it breaking into its ions like this are very unlikely. As this number increases, then your solubility starts to increase as well. Now on page 4, what we have here is we want to figure out what the solubility is. So this is code word for what is X. Now they can ask for the solubility in 2 different ways. They could have you figure out the solubility in terms of molarity, or they might want you to figure out the solubility in terms of grams. So I want to show you how to do both of these. Now, first, let's work on figuring out the solubility in terms of molarity. So what we are given is copper to iodate. So CuIO3 2. So first, we write our reaction. So CuIO3 2. That's my solid. Breaking into my ions. So I'm just breaking this up into ions. So it becomes Cu2 plus IO3 minus. I just uncrisscross my charges there. I make sure that it's balanced. You see that there's a 2 there, so I need to have a 2 here. Now I finish out my rice table. So this is 0, this is 0, plus x, plus 2x. Now I know that this is x, and I know that this is 2x. So now I write my Ksp expression. So Ksp is equal to, let's see, we have Cu2 plus times IO3 minus squared. Now, my next agenda is I want to plug in these expressions, and I have a K value, so I'm going to plug my K value in as well. So here we go. Ksp is 1.4 times 10 to the negative 7. My Cu2 plus is x, and my IO3 minus is 2x. Don't forget your coefficients right there, squared. So now I want to figure out what solubility is, so I'm going to solve for x. When I solve for x, because these are concentrations, my x value is going to be in terms of molarity already. So to solve for x, don't forget that you've got to follow correct order of operations and do all that good algebra. So look here, we have 2 squared, which is 4. X squared is x squared. And then I'm multiplying by another x. So that ends up giving you 4x cubed. So that is what is equal to 1.4 times 10 to the negative 7. To solve for x, I'm going to divide by 4 on both sides. And once I divide by 4, to get x by itself, I have to take what you call the cubed root. Now, if you know how to plug this into your calculator, you just take the cubed root. If you do not know how to plug a cubed root into your calculator, what you do is you take this answer and you raise it to the 1/3. So it would be whatever your number is, you raise it to the 1/3. That's your exponent there. That's also how you take a cubed root. Okay? So when you solve for that, you find x, which is equal to 3.3 times 10 to the negative 3rd, and that is in terms of molarity. So that's how we answer solubility in terms of molarity. Now the question is, how do we figure out what x is, solubility in terms of grams? When they want solubility in terms of grams, what they're looking for here is this solid. So here's what I do. I take this molarity, and I take molarity times volume. Well, what's molarity times volume equal to? Well, that's equal to moles. And if I know what moles is, I can solve for grams by using the molar mass of whatever this solid is right here. So I would say moles is equal to the molar mass, which is the grams, of whatever is the solid that I'm working with. So this is how you figure out your solubility in terms of grams. If you're trying to find it just in terms of molarity, then all you have to do is solve for x. If you're finding for grams, you got to figure out a little bit deeper. So you solve for x, take that molarity, and multiply by a volume that they will give you in the problem, get moles, multiply by the molar mass, and that gives you grams. So this is how you find solubility in both ways. All right? So I hope that was helpful a little bit. Remember, solubility just means X. And the way you do KSP, the way you set up your Rice charts, the way you write your Ksp expressions are the exact same way as you would any normal K value.